Okay, these are optional problems on pendulums. So, one thing we'll talk about today are a couple of equations. So I'm going to write those up here. The period of a pendulum is 2 pi times the square root of L, where L is the length of the pendulum string, okay, divided by G. So period depends on the length of the string or whatever rod, whatever's attaching the pendulum bob here, divided by our acceleration due to gravity. And then the restoring force for a pendulum, and I'll talk about deriving this one today in class, is this. So M is the mass, G is our acceleration due to gravity, L is that same length I just talked about, and then S is an arc length. This is like an amount that this would sweep out as it moves. So that's like it's a displacement for the pendulum, but it's not a linear displacement because the pendulum really doesn't move linearly. So we'll use these equations as we go through some of this. All right, assume 3 pendulums with the same length L. One is on Earth, one is on the moon, and the G value on the moon is 1.6, and one is on Jupiter. Jupiter's it's 26, it's big. So rank the period of these 3 pendulums from greatest to least. Well, looking at this period equation, okay, they all have the same length L, but G is different. So if I've got a smaller value on the bottom of this, I'm going to get a larger value for period. And so my pendulum that's on the moon, so I'm just going to call it TP moon, is going to be the greatest because that's going to have the smallest number here. I'm dividing by a smaller number, so this number is going to be bigger. That's going to make this number bigger. Okay, so the period of the one that's on the moon is going to be greater than the period of the one that's on Earth, because remember, for Earth this is just our 9.8 newtons per kilogram or meters per second. And then finally Jupiter, because it's huge, so it's got a much larger gravitational field strength. Why does a pendulum not oscillate in zero gravity? So if we look back at the period equation, okay, you have to have gravity in there. Acceleration due to gravity is part of period. It's also part of this restoring force, okay? So we know that we've got to have gravity in order to create that restoring force. The other choices, it still has mass, even if it's in zero gravity. It doesn't have weight or force of gravity, but it still has mass. These answers, I don't know, they just kind of don't really make sense. You know, like they're not. This wasn't the best answer choice because you have to have gravity. Acceleration due to gravity is part of the restoring force equation. And if you think about what's happening with the pendulum, I mean, gravity is pulling it down and helping pull it back towards the equilibrium position each time it swings from side to side. Okay, small sphere, mass M, is attached to a string of length L, so we've got a simple pendulum with a frequency of FO. Then we're going to replace that sphere with one that has twice the mass. And we're going to replace the string, so it's going to be reduced to half of the original length. Is the frequency the same? Okay. So this is where they've got a few different choices here. We need to look back at this equation again. So this is period, and remember, period and frequency are inverse, so this is going to determine frequency as well. Okay, what's included in this equation? Length and acceleration due to gravity. No mass. Okay, so changing the mass is not going to change the period and frequency of this pendulum, but changing the length is going to affect it. Okay, so we know that the frequency will not be the same, and we know that that's going to be because of the length. So it's going to be choice D. So we kind of narrowed that down based on looking back at the equation, and then we know that the mass isn't going to affect the period and frequency. It's going to be this string length that does. Okay, sphere is connected to a string set in simple harmonic motion. So this is a pendulum. It's released at 2 centimeters above its lowest position. So this is like equilibrium here. This is where it's released from. Shortly after release, the kinetic energy is equal to the gravitational potential energy of the sphere-Earth system. At this instant, the speed will most nearly be, okay, so this is a conservation of energy question. Okay, so what we're thinking about here is at our starting point, remember, you're going to have all gravitational potential energy. I'll call that HO, okay? And then at the point they're asking about, which is shortly after release, they're saying kinetic energy and gravitational potential energy are equal. So that would be like a halfway point. If you think about when we looked back at the skate park simulation. That's going to be a different H at that point, okay? So we want to try and solve this for velocity. Let's see if we have enough information to do that. We don't have any information on mass, but mass is going to cancel out. Blurp. We know that our starting height is 2 centimeters, okay? So I'm just going to start filling in values as I go. So we've got 2 centimeters. We got to convert that to meters, right? So let me get my calculator. So if I want to convert that, I'm going to divide by 100. I get 0.02 equals 1/2 times v squared. I'm solving for v. I don't know what that is. Plus 9.8. And then if I'm assuming this is the halfway point, then this would be 0.01 because I would have moved halfway down from that peak height. And so now I'm going to try and solve this for v and see what I get. So I'm going to do 9.8 times 0.02 equals 0.196 1/2 v squared plus 9.8 times 0.1, 0.98. I'm going to subtract this from both sides. I should get 0.98. Oh wait, whoops. What did I do? Oh. Hang on a second. I think I'm off a decimal place. Oh yeah, I see what I did. Okay, this should be 0.098 here. So then I'm going to subtract that from both sides. And I'm going to get 0.098 on this side equals 1/2 v squared. I'm going to divide both sides by that half. So again, I keep going back and forth between the same numbers. And then v is going to be the square root of 0.196, which is 0.196, 0.44. So the closest answer to that is 0.45. So 0.44 meters per second is going to be the speed at that point. So I used conservation of energy in order to do that one. Okay. taking gravitational potential as my, at my highest point, that's where it would have all gravitational potential energy, and then we're going to a halfway point, so we've got half kinetic, half gravitational potential, and it tells us that, like it tells us that we're going to have half of each, or they're going to be equal, which means they're going to have to be half of the total. Okay, I got a couple more, but this video may be getting too long, so let me finish up in the next one.